Hi, I hope you're having a wonderful time at PyCon this year. In this talk, I want to walk you through some aspects of healthcare and why Python is becoming the de facto language of choice in healthcare. My name is Akshay Sharma, and I'm the EVP of AI at Sharecare. Sharecare is a digital health platform that helps people manage all their health data in one place. Sharecare was founded by the same team that created WebMD, and we have rich history working in healthcare. I came to Sharecare by the way of an acquisition of a startup called doc.ai, where we developed products and models to understand and improve an individual's health. We built several AI-based technologies that allow us to capture health signals from users, usually using their phone. For example, we could extract medication information from pill bottles or extracting phenotypic information from video and audio signals. And then we use this rich real world data to train and deploy machine learning models in clinically IRB approved studies or even for simple engagement with the user. We extensively used Python for all of this. So to talk about the future of healthcare, we need to first understand the computational history of healthcare. For a long time, healthcare has been using a processing first thinking or processing first paradigm. And what I mean by that is it has mostly been about dealing with data formats and data exchange, and very little about data understanding. So you will often run into having to deal with exchanging data from one system to another, and you're mostly dealing with flat files or files with certain delimiter separated formats. A lot of investment in the industry has been made to just parse and format this data and put it in a database. So this is an example of an HL7 data feed of a person's medical record, and there are enough parsers to understand this data and extract information out of that. But mostly it's always been about data processing and very little about data understanding. Attempts have been made to standardize and facilitate data exchange. An example of that is continuity of care document, CCD. It has emerged as a standard with XML formatted data. Unfortunately, not all electronic medical record systems follow the same standards of CCD, so you have the information lost to some extent when you transform from one CCD to another CCD format. And there's also parts in the CCD that don't let you extract full information because it's completely text-based at some point. If you're lucky, some systems will support the emerging standard called FHIR, which has both a JSON and an XML view. And FHIR allows you to represent medical entities in a very structured way, where you can actually now write program and APIs around this data to not just process it, but also probably make use of it. Programming and processing such format is a lot easier, and you have very little information dropout if possible. In order to support such processing-based needs, some of the popular programming languages that have been used, and some of them are still popular, are COBOL, MUMS, and Java. Surprisingly, enterprises use a lot of mainframe, and COBOL is one of the top programming language that's used in on top of mainframe. So we are still in the world where we have to deal with some of the legacy systems in healthcare. And historically, the systems that have been built to deal with the processing nature of the data have been pretty complex and don't really support data understanding or building knowledge, but just mostly about taking data from one place to another. And so you'll often see things like enterprise service bus or legacy systems or J2E systems trying to access and process such data. So let's ask, what is changing in healthcare? We are seeing that healthcare is moving from a processing first paradigm to a compute first paradigm. And this is because what constitutes health data has expanded, and they're no longer in a central location as files or formatted files. You need to go to where the data is generated, and that could be on the edges. To explain this a little better, here is a point of view on what we are seeing from the computational trends. In the beginning, everyone built their own data centers, and used bare metal to process data. Then in 2006, Amazon changed the game by making cloud accessible for any company to be able to spin up a compute cluster and run your own processing nodes. We saw the dawn of monolithic apps on the cloud. By 2016, with Docker and Kubernetes already in place, we saw the trend of moving to much more of a microservice architecture where you have the smaller computes, but still have to access like larger data payloads. But what we are seeing now is the world of edge native, where we are seeing phones, sensors, MCUs, and neural network hardware are generating and collecting interesting types of information, usually on the periphery, some of which will not even centralize the data, but they just do predictions on the edge. We are truly entering an era of distributed computing. So the future, on one hand, looks like the hardware is scaling horizontally by having new products on the edge. And so is the software, if you look at it. So historically, we've seen monolithic apps become microservices with more distributed computing needs. And then we saw the emergence of something like machine learning and deep learning, which allows you to like build the algorithms out of the data. So you feed a lot of data and out comes basically your model. Model has some rules that it has automatically learned. So you're not programming the rules. But I think what the future looks like, because the hardware is going more distributed, the data gets generated on the edge, we are seeing that these models have to be compressed and actually sent down to where the compute happens, which is usually on the edge now. And for that, we are looking at like supporting tiny models that can do inference on the edges, but also learn on the edge. So the federated learning world has already emerged. So that's an important paradigm shift. And healthcare, we are absolutely seeing these trends emerge right now. So that's on the hardware and the software front. But healthcare itself is actually moving to a very distributed model. So pandemic has accelerated how care is being provided. So telehealth is now like the first point of contact in care. Clinical trials are going virtual and remote, where users can be anywhere in the country. We are removing geographic constraints, for example. That's a very important aspect of where the care can be provided. Gig economy is allowing healthcare workers to provide care at home. So overall, we are seeing the similar trends in healthcare where now there's more data being generated on the edge. And again, what this means is that everyone with a smartphone is actually generating certain health signals that can be used for understanding the health. And also what we know is that medical information doubles every 73 days. And what that means is that the only node that has up-to-date information and knows the most about you is actually you. And usually that means that it's somewhere on you, which typically is your smartphone. So taking a step back, what we need is a programming ecosystem that facilitates computing anywhere, given that the data can be anywhere. And Python is a perfect fit for this because Python can be run on the backend. It can be used for building web applications. We can also build and train models, which are really valuable in the case of healthcare. And if needed, we can also convert them and run on embedded systems using different variants of Python, for example, CPython. So let's ask the question, how is Python changing the computational nature of healthcare? And the short answer here is that by facilitating deep collaboration across all stakeholders that are involved in typically providing care and research. So traditional healthcare systems are very siloed. The data creation systems and teams are isolated from data transformation systems and teams. So you go from one environment to another environment and at times jump system boundaries where knowledge in the data gets translated into outside the scope of programming environment. So it goes into Word or Excel. And these are lossy transformations because it's usually one way and there is absolutely no feedback loops back to how to improve your algorithm or the code. And the stakeholders are not collaborating in a single system view. So finally, when you want to derive insights from the data, you are crossing several systems and you've lost certain information It's almost like playing a telephone game of medical knowledge. So here is how we are seeing the modern healthcare stack work by bringing all the stakeholders onto a single data-driven point of view without having to jump the different system boundaries. You could still be doing the physical system boundary jumps, but logically it's single system view. We call this data fluency, which allows all the key stakeholders to discover the value on top of the data or insights on top of the data in real time and in an agile, iterative way. And all of this is powered by a notebook behind the scenes. So to walk you through what that looks like, it starts by building one or more notebooks on top of the data. This could be our data engineer or data scientist for building transformations, and then obviously building models on top of that. Or it could also be simple analytics. The knowledge on the data is contained in one single place, which is a Python notebook. Now, the finance or the operations person is looking at the same insight on top of the data that is derived out of that notebook, and it's generated on top of the same algorithms that were self-contained. And more importantly, they can actually give feedback based on using tools like this, which have been generated on top of the data. So what they see and what they want to change is actually an active feedback back to the data scientist, where you can go back and update your notebook and you can have a new version almost instantaneously. You do not have to wait for knowledge getting translated to a Word file and then some product manager having to come back and rewrite that as spec, and engineers going to have to build this. That cycle has actually rapidly reduced by having a notebook-based viewpoint. Now, what about clinicians and care management teams? It's actually indeed the same system. The views that are generated here are also from the same Jupyter notebook by slapping in a UI app. There are no new systems or teams building insights in silos. Again, the feedback from the care management team is immediately incorporated back into the notebook workflow. So in the end, what you have is multiple views to discover insights on the data from different stakeholders, but everything is powered by the same set of notebooks, and that continues to learn and improve over time. So, and in order to support such workflow, data fluency workflow systems, you almost need to invest in certain advanced AI and data fluency workflow systems. The system is designed for agility of computing on data and extracting knowledge. Thankfully, a lot of cloud native architectures allow us to do this. A lot of this can actually be automatically extended to like computing on the edge, and I'll show you some examples of that. End of the day, send me a notebook is now the new currency of medical knowledge. Let me phrase that again. Send me a notebook is the new currency of medical knowledge. What we are seeing is that everything starts with a notebook. You write a program, you write a model, you express the model in different views for different stakeholders. You actively learn from their usage and feedback and continue to improve the algorithm all in one place. And that's the most important thing that we are actually seeing in healthcare right now. So I talked about how healthcare has moved from a processing first paradigm to a compute first paradigm. But where we are actually seeing the future go is deriving intelligence on top of the data and keeping the data private. A lot of this happens with users on their phone and using their personal devices or other sensors at home. So privacy is actually a first-class citizen in the context of healthcare, in my opinion. So we are entering an age of understanding health using dry, novel digital biomarkers that can be captured and extracted using the user in the loop. So historically, healthcare has looked at a lot of sequencing data, what we call as wet biomarkers, molecular sequencing or DNA sequencing data. But I think the new world is also augmenting that by bringing in interesting characteristics from data that can be collected from images, audio and video data feed. So we can extract certain information there and see the correlation of that to certain conditions. We can do this on edge devices like smartphone, for example, and we can predict using AI models on the device And if privacy is of importance, we can leave the data on the device and improve the model on the edge using federated learning. We will see many sensors at home and at hospitals in the future that is collecting interesting information like this. Then finally, of course, we can use machine learning if we can centralize the data to actually build certain models and then compress them back and send it down to these edge devices if need be. So I'll give you a few examples of what this looks like. So nail psoriasis is an example of where basically you have certain discoloration of your fingernail, and it's the growth of psoriasis, the condition. So it can be measured looking at a fingernail by separating it into 4 quadrants and seeing if there is evidence of psoriasis changes on each of the 4 quadrants. Then you add up all of the 4 quadrants across 4 of your fingernails, so you exclude the thumb, and then you come up with a score from 0 to 16. And based on the score, you know whether the person actually has psoriasis that continues to grow. And this is an old school way of doing things. It is simple, it was standardized, and it actually is pretty effective and it's being used. The only caveat is that this requires you to go to the hospital with a doctor every time you need the diagnosis done. So now imagine, can we ask the question, is this automatable? So what if we can take a picture of the 4 fingernails and use a computer vision model to see the discoloration and compute on the smartphone the NAPSI score, the 4 quadrant scores, and do what a clinical site person would do. Now, we all know that there is already enough AI power or sort of technologies that allow us to like look at certain vision images and be able to understand what's in the image. This would probably be a CNN, convolutional neural net, that we can implement. But the question to ask is, can we do better than those 4 quadrant way of looking at things? What if we could look at and observe growth in much smaller regions within the nails and actually understand the growth of psoriasis and come up with a better score if need be? So our ability to improve on the clinical grade of the old school methods, the manual way of data collection, the simplistic and subjective ways of measuring the NAPSI scoring, into something that is much more objective, automated, nuanced, high fidelity, and that can be done at home without requiring continuous sort of site visits, is what is exciting about this. And this is a great example of one such digital biomarker that can be done on the phone. Let me give you another example. And this is in fact something we have launched as a study, and by study, it's a clinical trial. Myasthenia gravis is a neuromuscular disease that is relatively rare, and it's so hard to find and recruit people. But on the phone, it is much easier to recruit because you can open it up to anyone in the country to participate. So even though there are fewer people with the condition, but the fact that I can look at a wide geography and let the convenience of a smartphone at home let them participate makes it a lot more tenable for people wanting to participate here. So in this study, what we are looking for are subtle changes in the voice, and also things like eyelid drooping as markers for the condition. The hypothesis of the study is that a selfie video that captures both facial characteristics and auditory or voice characteristics can lead to a much better score of clinical progression or regression of the disease, allowing people to record selfie on a daily or a weekly basis with some frequency, with some common phrases, utterances, whenever they would like to do it at their convenience, would allow us to actually bring that data with the right opt-ins and the right privacy constraints and understand what's going to happen inside the data to the condition. And this is actually transforming research, in my opinion. So here's what we have observed, right? So the plots show on the left basically show that there is the eye height to width ratio for 3 participants. So all the way on the left are control groups of patients who do not have myasthenia gravis. And on the right, images of the eyes, you will see that they are they are plots from basically they are images of people with myasthenia gravis. Of course, these are not the real images. These are public images that we've used, not from the study. But what you're seeing there is that we are able to look at the ratio and train a model of the height to width of the eyelid and compare that both on the left and the right and see if there are lags. So that allows us to understand if a person with MG actually indeed has certain of those symptom characteristics. And now we can ask the question, can it be predictable based on certain other phenotypic and other types of data that we are collecting as part of the study. Similarly, we are evaluating if there are speech pattern differences for certain keywords that these patients actually utter on a daily basis, and we are trying to evaluate to see if there are ways to predict somebody with certain speech occurrences could have patterns for MG, and we are indeed seeing some sort of correlations there. So, but where is Python here? So, as expected, the study models are actually written in Python, and in this case, using TensorFlow, which is a Python library that we use extensively at Sharecare. It is a custom neural network based on top of convolutional neural network to understand from the temporal data of the video feed. So this is the model that we are actually using for understanding the droopiness of the eyelid. Similarly, the audio model is also a Python based model based on TensorFlow that analyzes the speech using a convolutional neural net, 2D convolutional neural net, on top of a spectrogram. So we take the audio data and convert that to a vision problem, which is pretty standard in how CNNs are being used for understanding speech. And of course, there's a certain custom FFTs that allow us to extract certain information. What I want to caution here, though, is that these models require extraordinary clinical rigor. This is a study, and it's IRB approved and is run and validated by clinicians on staff. So one thing to be aware of in healthcare is you just cannot build a model and launch it. You need to go through the rigor of clinical testing and bring in the safety, including the patient safety and data safety, in order to bring it to market. So that's what we are working on. And the final example I want to point you to is towards what the community has built. When the pandemic started, many asked the question, could we detect cough sounds using phones or devices? You can build such a model using Python and TensorFlow Lite with the microspeech model. So if you Google, you'll see enough examples of people having built COVID-based or even just cough detection models. The intuition of how to go about doing this is what I'll explain here. And it's by doing transfer learning on the microspeech model and training it to learn cough sounds. So microspeech model is a model that's open source and available on Google Colab. And it basically has learned yes, no words. You can always extend it to train on other types of words, including a cough word. So you would collect enough cough samples and label them as cough. The hardest part in healthcare is how do you go about collecting the critical data to make this happen? And that's where you need to invest quite a bit in app experiences and trust and safety with the users to let them participate in this. Then once you have enough labeled cough data, you retrain the model with newly added labels and add the cough data on top of that to train the model. Then, of course, you need to validate the accuracy of the model. And maybe you have certain additional cough data sets that you use for testing and validation. Now, what you have out of that notebook, all of this can be done on the Google notebook that's been linked on the slide. You can actually generate a TF Lite model, which is TensorFlow Lite model. And the Lite model actually lets you run it on the phone. So we have built some tools like TensorIO that lets you take that model and run it on the phone if you need. But where it can go even further is taking the TensorFlow Lite model and basically compiling that to a TensorFlow micro model. Again, that the notebook lets you walks you through how to do that, and actually deploying that on embedded devices. So devices that's beyond the phone where TensorFlow Lite doesn't run. And there are additional links out there that you can actually look at how it's been done. The question that always comes up though is how can we improve a model like this but by keeping the data private. You don't want the user's data to be centralized on a server, other than the fact that you built certain baseline model data for building the model, right? So there are some tools at our disposal to take privacy seriously. So federated learning, differential privacy, and encryption techniques like including homomorphic encryption and secure multi-party compute are some tools in our bag to do that. Now, not all of them run on the phone, given the complexity of the things. But what I can tell you is that with federated learning, we've already cracked that problem where you can run this on both iOS and Android phones. So you can keep the data on the edge, usually the phone, and just improve the prediction scores on the model by aggregating the tensors or the gradients on the cloud. So you have a model running on multiple users' phones. They are doing predictions, but then you could train the model individually on these phones to new data that the user is collecting that's just on the phone. And as you do that, you can then have the model send the gradients or basically the trained new weights back to a server, and you aggregate those weights in different ways, and you have a new model. Empirically, the question is this model better? And what we are seeing in real world is some of these models are actually improving. So we have built tools that allow you to do this. All of this, again, is Python based. So you can look at our GitHub repository, but I'll also call your attention to the fantastic team at OpenMind that is building like a lot of these tools using PyTorch. So they have done some phenomenal work that I'd encourage everyone to look at. So the final key takeaway here is that the world of healthcare has moved from a processing first thinking to a compute first thinking. Compute can be anywhere, cloud, phones, or tiny sensors. Compute allows you to build gradients and intelligence on top of the data. And privacy will be a first-class citizen when it comes to healthcare. And the good news is that every one of you here with your Python knowledge and background can actually participate in healthcare. It all starts by building notebooks. So I want to end this presentation by motivating you to think about some hard but tractable problems, a lot of which healthcare has to offer, where your Python skills will actually make a difference. So privacy on the edge and biometric markers on health are just two examples of what I'm involved in, but there are other interesting ideas such as NLP for text understanding on doctor's notes or nurses' notes, for example, or understanding call center data for people who are actually talking about their healthcare concerns. And of course, we are seeing voice-based systems now going into provider places where they're using voice to translate notes into structured data. So there are interesting problems, and a lot of that can actually start with just a Python notebook. And I would love to see many of you take on such challenges. Thank you so much. If you're interested with what we do, please follow us. And I hope all of you are having a fantastic time at PyCon. Thank you.